So this video will show how to find limiting reactant, theoretical yield, and percent yield using stoichiometry. So I want to go over the summary of terms first. So limiting reactant, or sometimes it's called limiting reagent, is a reactant that is completely consumed in a chemical reaction. So in other words, limiting reactant is the one that runs out first, and the other reactants will be left as unreacted. And theoretical yield is the amount of products that can be made in a chemical reaction based on the amount of limiting reactant, because it's going to run out first. It can be a mole or it can be a mass. And actual yield is the amount of product actually produced by a chemical reaction, usually in a lab or in a plant that produce certain chemicals. And actually that is usually given as a mass, because that mass is things that we can get easily in a lab. And percent yield is the actual yield divided by the theoretical yield times 100, because it's a percent. And if the actual yield, the chemical produced, is pure, the percent yield is not going to be more than 100%, but actually in a lab setting, sometimes the percent yield is bigger because the chemical produced may not be pure or may not be dry enough. So percent yield can be more than 100% in those cases. All right, let's go into how to do this kind of problem. So in this case, I'm gonna use A plus B equals C as a reaction scheme or chemical equation. And in this case, A and B are the reactant. So usually mass of A and B are given, and you have to find out which one runs out first. So there are different way to find out, but I find this step one is most useful. So you have to, again, if the mass of anything is given, you have to convert it to the mole, right? So mass of A convert to mole of A, mass of B converted to mole of B. Then from this chemical equation, you're gonna put into the conversion to go to product, because that can be made from A plus B, both of them. So from chemical balanced chemical equation, assuming this is 1A plus 1B is 1C, then mole of C, ratio of mole of C and mole of A is the conversion factor to convert mole of A to mole of C. Similarly, from the chemical equation, you find out the ratio of mole of B to mole of C. And if needed, you can calculate the mass of C by using the molar mass of C. But to just find out the limit, which one is a limiting reactant, you can just compare those two, mole of C's. Then smallest amount of mole of C is gonna be determine the limiting reactant. So if mole of C from mass of A is smaller than the mole of C from mass of B, you can tell A is a limiting reactant. And if mole of C from the mass of B is smaller, then you can say mass of B is a limiting reactant. And of course, you can compare the mass of C directly also. Then, so that's a step 2 already. Then the quantity of C, either mole or mass, from the limiting reactant is the theoretical yield. So if you determined A is a limiting reactant, then mole of C and mass of C from this is the theoretical yield. And there are situations that you were given the reaction that's going to produce 2 or more products. Then just pick one product to calculate the limiting reactant, so either C or D in this case, and determine the limiting reactant. All right, let's try to do the actual problem. Practice 8.3, question 1. In the reaction, so again here, the chemical equation is given. Make sure this is balanced, then you can use it. So this is Fe2O3, iron 3 oxide is reacting with aluminum solid and producing iron solid and aluminum oxide. So once you are given the mole of each, that's the thing it's given, you can calculate the mole of product. In this case, the aluminum oxides are given as a output. So you have to find the ratio, mole ratio from this equation to find the mole of aluminum oxide. So mole is given, output is mole. So the only conversion factor you need is the molar ratio from this chemical equation. And because given mole is Fe2O3 here, look at this, Fe2O3, there's just 1 mole here. And the mole of aluminum oxide here is just 1 mole aluminum oxide here, so 1 mole of aluminum oxide is a ratio, it's a 1-to-1. But you have to have this conversion factor to get to the mole of iron oxide to mole of aluminum oxide. So 4.5 mole times 1, so 4.5 mole of aluminum oxide will be produced from 4.5 mole. How about the aluminum side? So aluminum, 8.7 mole of aluminum, then conversion factor from the thing is, okay, so that's wrong, so I wrote it too fast. So mole of aluminum is down there, and you find that it's a coefficient as 2, so 2 mole of aluminum will produce 1 mole of aluminum 2 oxide. So now you're going to divide the 8.7 by 2 to get to the 4.4 actually. So which one is a limiting reactant? So you compare these two, smaller one, pick the smaller one, and producing smaller one is aluminum actually. So even though molar amount of aluminum are given bigger, actually it's going to produce smaller amount of aluminum oxide. So aluminum is the limiting reactant here. All right. Then how many mole of aluminum oxide can be produced from the condition in part A? Because you already calculated 4.4 mole of aluminum oxide will be produced from aluminum, 8.7 mole of aluminum. You can say it's just 4.4 mole of aluminum oxide. So that's a mole to mole. Then we can do the gram to gram question. All right. In the reaction, 2Na solid plus chlorine gas gonna produce 2 NaCl solid. All right. And which reactant is limiting reactant if 53.2 gram of sodium and 65.8 gram of chlorine are mixed and allowed to react? So the two reactant mass are given. So we're gonna have to start from there. And then if the mass is given, you have to convert to the mole. So to do that, you need a molar mass of sodium, which is 23.00 gram of sodium is 1 mole. And remember, it's divided by the molar mass. Now you have a mole of sodium, and you have to go back to the equation, chemical equation, to get the mole ratio of sodium, and in this case product is sodium chloride, and actually the output is already given as a mass of sodium chloride. You're gonna convert it to mole of sodium chloride from mole of sodium, and which is actually 2 mole of Na gonna produce 2 mole of sodium chloride, because those two coefficient. You can just put one to one if you are sure about that, but I would use just exactly the coefficient there to make sure I am putting everything from the chemical equation. Then you got the mole of sodium chloride. The last thing you want to do to get to the mass of sodium chloride is to have a molar mass of sodium chloride and use it to convert to sodium chloride mass, which is 58.45 gram of sodium chloride will be the mole of sodium chloride. Again, I want you to make sure everything, this setup is correct by checking those units. Gram Na cancel, mole Na cancel because they are in the opposite side. Mole of sodium chloride cancel, and then you get to the gram of sodium chloride, which is, if you put everything in there and round to the correct significant figures, it's going to be 135 gram of sodium chloride from 53.2 gram of sodium. You do the same thing with chlorine. Just make sure you put the correct molar mass for the chlorine gas, which is Cl2. So the molar mass will be 70.90 gram of Cl2. It's going to be the 1 mole of Cl2. Then you're going to put the ratio of sodium chloride and chlorine gas, and then chlorine gas in the chemical equation doesn't have coefficient. That means it's a 1 mole of chlorine gas. So that means every 1 mole of chlorine gas will produce 2 mole of sodium chloride. Then you convert this to mass because that's the asked output. The molar mass is the same, so you can just put the same molar mass here to convert the mole to mass. And before doing calculation, just making sure all those canceling units are opposite side. Then if you do that, you are getting 108 as a output answer, and you're gonna compare those two to find out which one of those are the limiting reactant, because the output from the chlorine gas is smaller. Chlorine gas is the limiting reactant. Make sure you answer as a chlorine gas as a limiting reactant, because those are product. So make sure you answer using the right term. And then once you know that, it will be easy to answer the next question. because how many grams of sodium chloride can be produced from the condition in part A, and then we determine the limiting reactant, and then we determined it's going to produce 108 gram of sodium chloride. So you can just put 108 gram, 108 gram of sodium chloride here. So that's a theoretical yield, because actual yield is lab yield. That's not a calculated yield. So this is a theoretical yield. So sometimes a question asks what is a theoretical yield in mass of sodium chloride, something like that. Then you will know what they are asking. So if the actual reaction produces a 86.4 gram of sodium chloride, what is a percent yield? So conveniently, the equation is given here. So actual yield is this guy, because actual reaction yield, right? 86.4 grams sodium chloride. And then if the reaction is super efficient, it's every single molecule of chlorine gas converted to the product, it would be 108 gram sodium chloride. And because it's asking the percent, you do this, and you get 79.6 percent is the percent yield of this reaction that you did in a lab. So in this case, the percent yield is smaller, so it's gonna, you didn't convert 100%. All right, so that is it for how to find limiting reactant, how to calculate theoretical yield, and find the actual yield. Given the actual yield, you can calculate the percent yield.